Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll look at naive Bayes classifiers and specifically look at what is naive Bayes. Then we'll look at the Gaussian and the multinomial naive Bayes classifiers with examples, and then we'll look at the uh, complement, Bernoulli, and categorical naive Bayes, the mathematical relation for those, and finally I'll mention what the out of core naive Bayes is. So here is one reference for further reading, which talks about the naive Bayes text classifiers. So what is naive in naive Bayes? So why naive Bayes? And the reason is here, on one assumption is made that the features are independent, so there's no interaction between the features, and in real world scenario that may not always be the case. So that's kind of saying that that's a naive assumption that is in place while working with these classifiers. Therefore the naive Bayes classifier, and we can look at that in more in further detail with these relations. Let's look at an example where we have shown in table on the left. We have these features: weight of maybe this could be any fruit, say apple, then sugar content, size, diameter, and the defect, is it insect damage or no defect or pressure damage, and then is that particular apple sellable, 1 if it is sold and 0 if it is not sold. So all these features can be represented by the Bayes equation as shown here, where we have the posterior of y given the features is equal to the prior, which is prior for the classes, um, multiplied by the likelihood divided by the marginal. Now here we have this likelihood, which can be expanded in this form, where we have p of xi given y, x1 y1 x1 x2 all the way up to xi plus n I plus 1, and that can be, if we assume conditional independence, then we can reduce this to p of xi given y, and when we plug that back in the numerator, we can represent it as a product of these conditional probabilities of xi given y. And when we are looking at to get the posterior probability for each class, now when we are looking at the posterior probabilities for each for the two classes, or maybe more than one two classes, the denominator would be the same, which is this one. Therefore we can ignore that, and we can use just the numerator of the right hand side with a proportional sign to look at the posterior, and therefore the classification rule or the decision rule then is whichever class has the maximum value of this right hand side term is the class to which that particular data point would belong, or that particular sample row vector would belong. So that's the idea of the naive Bayes classifiers. Now let's look at a Gaussian naive Bayes classifier. Here, let's look at the table on the left hand side first, and here we can see that we have the weight, sugar content, size, diameter. So these could be the values for fruits such as apple, and as you can see all these values are continuous values. The final output target is categorical because we are using a classifier now. Now for naive Bayes, what the steps are is that we can separate these by classes for each of the features. So this is for weight, we have class 0, the fruit was not sold; class 1, it was sold, and we get the mean and standard deviation. And same way for the sugar content we get the mean and standard deviation. For size we get the mean and standard deviation. Now, the reason why we are getting the mean and standard deviation is because using those we can plot a Gaussian curve, the normal distribution, and then we can estimate the likelihood from that. So before we get into that, one point we need to be clear on is what is probability versus likelihood. Let's look at this example of just one feature, which is weight for the class sold and the class not sold, which is 0 is not sold, 1 is sold. If we use these mean and standard deviations to plot the Gaussian distribution, we get a plot that is shown here on the right hand side. So 86 would be the mean for the orange curve and 73 would be the mean for the blue curve. Now, when we, and on the x-axis we have the weights, y-axis we have the probability density. Now, when we talk about probability, the way we would phrase the question would be, let's say, if we want to know what is the probability that the weight of the apple lies between 90 to 80 grams. So, within this particular shaded range. So to get that value of probability, we need to get the area under the curve for that region, and that here is 0.09. So probability that the weight of an apple lies between 90 to 80 grams given the mean of the distribution is 86.75 and its standard deviation is 7.4, then that probability is 0.49. Now we assume that we already have a data point. So we already have the weight of the apple, which is 90 gram, and we are looking for the distribution from which, the likely distribution from which this data point would have come from, or to which this weight would belong. And so here, if we look at 90 on the x-axis and reach up to the orange curve and look at the magenta dot, and then we could look at the corresponding y-axis value, that would be the likelihood. In this case, it is 0.043. So the way we would read this is that the likelihood of a distribution with mean of 86.75 and standard deviation of 74 given the weight of the apple is equal to 90 grams is 0.043. So that's what we are going to use to calculate the Gaussian Naive Bayes likelihood values. So again, we have this data point where we have the weight, sugar content, and the diameter of an apple, and we are trying to find if that apple would get sold or if it does not get sold. So does it belong to the category 0, which is not sold, or category 1, which is sold? Category or class. And again, this is the same feature. So what we are going to do is uh, create the Gaussian distribution based on the mean and standard deviation for each of the feature for each of the classes that we have. So we have two classes, 0 and 1. So we have the distributions for those. Then we take the value for the test feature that we have. So in this case, we have the weight. We look on the x-axis for the weight and get the corresponding values for the likelihood. So that's the first point. First, we look at just class 1, which is the orange curve. And so the next one, we get the value for sugar content. The likelihood is 0.23, and the diameter for 70 millimeters, and we get likelihood of 0.01. Similarly, we then look at the likelihoods for the class 0. And because the blue curve drops right here, close to 0, therefore the likelihood in this case is almost 0, which is represented by a value which is e to the power minus 9, so very, very small value. And this is a typo here. And for sugar content, we have 1.10, and for the size we have 0.09. Now when we look at mathematically, uh, the way we would read that is for each of the classes not sold and sold, for weight what we have found is the likelihood that the weight is 90 grams given that it belongs to the class not sold. And similarly for here we have likelihood that the weight equals 90 grams given that it's class sold. And these are the values we have: 2e to the power minus 9, 1.10, 0.09, and then values for the sold. Now in this we also know the priors. Priors is what is the probability for each of the class to exist. So total, if you look at the all data points, the main plot right here, we have 1, 2, 3, 4 samples that belong to class 1 and 2 samples that belong to class 0. And in total we have 6 classes. So the prior for the class 0 would be 2 by 6, and the prior for the class 1 would be 4 by 6. And that's what we have in this table. So we have 4 by 6 and 2 by 6, each of those probabilities. Now we are going to calculate, if you remember the right hand side equation of the uh, uh, Gaussian, the naive Bayes that we looked earlier, we are calculating the likelihood here. So prior multiplied by likelihood for the weight is 90 given class is not sold, and all this is for sugar and size for class not sold. We are plugging these values, so 0.33, then 2e to the power 9, 1.10, 0.09, and then next step what can do is we can take the log of this to avoid an underflow problem. What that means is if we have a very small values that are close to 0, such as this one, then it could create a problem where the computer cannot keep track of these small numbers, and therefore we are taking log of those so they can be easily worked on. So here we have, when we take a log, we can these multiplication signs turn to additions, and then we get a value of minus 23.45. Similarly, we can calculate the values for the class sold. So probability of sold, so that's the prior multiplied by the likelihood of weight given the class is sold, and then similarly for sugar content and the size diameter. So here we plug in the values from this table right here. We have 0.67, then we have 0.43 that goes here, 0.23, and then 0.01. When we take again the log and find the value is minus 9.62. And so what we have is, because the value of 9 minus 9.62 that belongs to the class 1 which is sold is larger than the value for the not sold which is minus 23.45. Therefore we can classify the data point to class 1 which is sold, and therefore to answer our question, does this apple get sold, the answer is yes, it does get sold. Now we can look at visually how that could look. So blue represents the apples that were not sold, orange represents the apple that were sold, and the magenta dot shows the apple, the test apple that we classified that it would get sold. And here we can see that it is far away from these orange data points, but it's still in on that side. So if we look at from the other side, you can see that it does belong to this side of the group rather than on the other side. And I looked at couple more angles. So it's a 3D plot. So you could rotate it and see which angles it gets closer to. But even if you see that it's on top of the blue dots, you can still, in those cases, you can see that still you could separate the orange dots from the blue dots. So maybe that's a correct class to which it would belong. Now the next method that is available in scikit-learn is a multinomial naive Bayes classifiers. So this is mostly used in text classifications where the data is, the features have the data which is counts for words, and it is given by this relation shown here, where the theta is the maximum likelihood which is smoothed by this parameter shown here in the teal color. So essentially what it says, it's a ratio of count of occurrences for a word in class Y divided by total counts of all the features or all the words in class Y. That is denoted here by NYI divided by NY. And the smoothing parameters are shown here. They can be greater than or equal to 0 or less than 1, and based on what type is chosen. And n denotes the number of features or the number of words in the vocabulary for a document. So what I mean by size of a vocabulary is, let's say you have a document that could be just a sentence of uh, 3 words. This is a slide. Then the vocabulary would be this, is, and slide, 3 words. Now this theta is the probability of xi given y. That's the likelihood. And here, as an example, let's look at this particular table on the left hand side, where we have text, document, and class. So let's assume that each row is a document. So people enjoyed football match. For this example sake, let's think of that sentence as one complete document. And then the second document is people enjoyed cheeseburger, and the third document is people love football. Now the first and the third document is belonging to class sports, and the second one belongs to class food. So the task that we could have is, we need to train a model based on this information, and when we get a new document, we need to classify that either as belonging to the class sports or class food. So to begin with, we can find the priors. So priors in this case is total, we have 3 documents, so denominator we have 3, and then for sports we have 2 documents that are sports, so 2 by 3 would be the priority, the prior for class sports. And then for food we have 1 document, so the prior for food would be 1 by 3. And on the right hand side table we have the values for probabilities. Probability uh, for the word people, given the class is sports, a probability that the word is enjoyed given the class is sports, and so on, and for the other food as well. So the first, we have this equation, and so in this case we'll assume alpha of 1, and the vocabulary size here we have 7 words, 1 2 3 4 5 6 7, so that's why we have the 7 there. Now, so here we have in sports class we have 2, the count for the word people is 2, and therefore we have the 2 there. The count for food, count for people in the class food is just 1, so we just have 1 people here, so we have 1 here. And then the total is 3 for the word people in all classes. Similarly, the word enjoyed occurs only once in the class sports. up in this row and it's not there in this row. So just one value here. The enjoyed word appears once again in for class food, which is the second row, and so we have one here, and therefore the total is 2, and so on for the rest of the documents. So the word burger appears only in the class food, so we have 1 here and 0 for the class sports. So the total is 1. Now we can use this to calculate these probabilities right in this chart using this formula above. So for people we have 2, which is right this 2 plus 1 divided by 7 plus 7. So I've multiplied 1 into 7, which is 7, so I'm just putting 7 here. And then for food we have 1 plus this 1 divided by 4, because here we just have 4 words in the class food, 1 2 3 4, so we have 4 plus 7, and we perform that for all other words in the vocabulary, and then we get these fraction values which can be converted to these. So these are the probabilities for all these tables, all these values in the table above. And now what we can do is use those values to calculate the probabilities likelihood for the new test text document. So the new document we have has these words in it. People enjoyed football, football. So what we can now do is calculate the probability for the class sports given this particular document test, and the probability for food given the document test. So here we have 0.67, which is the prior for sports, multiplied by 0.21, which is for people, and there's people here. So we have people from sports, and because it's just occurring once, we have raised to power 1. Then we have 0.14 raised to power 1 for enjoyed, the word enjoyed, and for football we have 2 football words, and so we have 0.21 that comes from here raised to power 2, and so the value is 0.0009, and instead of equal to we have a proportional sign here because we are calculating the posterior probability towards given test. And again on the right hand side we have the prior is 0.33, which is here, and then for the word people we have 1.18, and that's here. For word enjoyed we have 0.18, and then for football we have 0.09, which we are here, and when we multiply this we get a value of 0.00009. And if you look at the Scikit-learn implementation source code, in addition to this there are other transformations to this. So there is log, there's normalization, which we are not doing here, so these values may not exactly match what output you will get in if you run this in Scikit-learn, but this is just to give you an intuition of how how multinomial naive Bayes could be working. So once we calculate this, then we can look at the probability values, and here we can see that the probability for this document belongs to class sports is higher than the class food, and therefore we can classify this document as it belongs to the sports class. And this document could be anything. It could be a book, it could be a magazine, or a news article that we are trying to classify. Next, a complement naive Bayes is similar to the multinomial naive Bayes, except that instead of looking for occurrences in the class that we looked at, we are looking at the occurrences in in the other class. So count in this formula we have count of occurrences for a feature or word in classes other than C, and below we have total counts of all the features or words in classes other than C. So we leave the class in which we are, and when we look at the numbers in other classes, then it still has the smoothing priors, the same as before. And this is the summation, n is summation, so that's uh, written out here explicitly. And based on this, then we can calculate the weights. So this is taking the logarithm, as I mentioned in the last slide, and then this is normalization. So this is also called the weighted normalized complement naive Bayes, and then this is then used to calculate the values for classification. So in here we are looking at the minimum values for classifying the data point to a particular class. Now, a Bernoulli naive Bayes, in this case, uh, generally the features would have binary values, and this is the classification rule for the Bernoulli naive Bayes, which is p of xi given y is equal to p of I, where I is the feature, y is the class, into xi plus 1 minus p of I given y into 1 minus xi. Now in the categorical naive Bayes, this is again the equation we have in the middle. These smoothing priors are similar. The difference is for the values of n in the numerator and denominator. So the numerator now is the count of occurrences of the category T in sample X for class C, and the denominator is the number of samples with class C. So this gives us the probability of category T in a feature I given class C. So Y is equal to C, so that's the class C, and XI is the feature with the category T. Now, out of core naive Bayes model fitting is feature. It's feature available in Scikit-learn that we can use with multinomial naive Bayes, Bernoulli naive Bayes, and Gaussian naive Bayes. And where it helps is if you have a very large data set that cannot fit into memory. In those cases, the partial fit method can be used for batch processing. So that could be helpful in case of large data sets. And finally, for code snippet, we have a new library which is Scikit-learn. From Scikit-learn import naive Bayes, naive underscore Bayes. And for data sets, we have the xtrain, this array, ytrain, and so each column could be uh, the counts for the word people, food, enjoyed, football, match, cheese, burger, and each row could represent a document, and the y is the class to which each of those rows belongs. So one could be sports, two could be, the zero could be food, and then again sports. Then we have a test document with the counts for the words that are listed above. Then you can use the multinomial naive Bayes to fit it on the train set, then predict for the test set. Now let's get into Jupyter Notebook and see how we can code some of these. Here in Jupyter Notebook, I've imported these libraries: NumPy, Pandas, Matplotlib, and naive underscore Bayes from the Scikit-learn. Then these are the versions. For data, so there's something wrong there. Let me stop this and restart this kernel, and we'll run this again. So running this. Okay, so now we are good. And for data, we have a couple of data frames. This one is df1, and that for df test one with the word count for words, similar to what we see in the discussion earlier. And then for Gaussian, we have these numbers. Again, this is similar to what we have seen earlier. Is the weight of apples, maybe sugar content, size, there's diameter, and the category if it's sold or not. So we'll use these to perform the modeling. So the first item that we look at then is, so we'll model, and this is uh, categorical. So categorical features. So we'll look at the text document, and for this then we'll use the first data frame, which is the df1 and df test one, and to make it into array, we'll create a variable x underscore train is equal to np dot array df, and then y train is equal to np dot array, and here we have 1 comma 0 comma 1. So we have sports, food, and sports, and then x underscore test is equal to np dot array, and this is df test 1, and this should be df1. And then we have y test. So y underscore test is equal to np dot array, and this is 1. So this is the sports, and here we have sports, food, and sports. And so these are the classes we have, and we can print the shapes. So print x underscore train dot shape, x underscore test dot shape, y underscore train dot shape, y underscore test dot shape, and so df1 is not defined. That's because I won't run the cells yet. So these are the shapes we have. Now to fit the models, we'll create a model list. And I know this is a toy example and not the actual test classifier example. We'll work on a project in a separate video. So here, this is just to get the steps in place for how to implement the Bayes classifiers. And then we can use that knowledge to work on a bigger problem. So naive underscore Bayes dot multinomial naive Bayes, and we'll leave the default values multinomial naive Bayes. And then the next one is, so we go to the next one. So this is naive underscore Bayes dot categorical naive Bayes, and this particular model gave me an error earlier, so it will comment this out later on and use a different set of data for this. Next, after this, we have naive underscore Bayes dot Bernoulli naive Bayes, and this has a feature where it can convert the features into binary if they are not already binary form. BernoulliNB Bayes, and then we have naive underscore Bayes dot complement naive Bayes, and so here we write complement naive Bayes, complement with an e. And so with that, then now we can move on to the for loop part of here. So for CLF name in model underscore list, we can print this is just a line to for visualizing the separate results. You can print the name and again print the same line down below, and once after that. So within this, then we can write clf dot fit x underscore train y underscore train, and we have y underscore pred is equal to clf dot predict y x underscore test, and we just have one sample there, so won't get the matrix. We'll simply just look at the predicted values side by side. So y underscore test, that's the actual value we have given, and then y underscore pred, this would be the predicted value that we'll get. And so now when we run this, so we get a prediction class is 1, which is sports, and the actual class was 1 sports, so that's good. Now here for categorical naive Bayes, this is an error. Index 2 is out of bounds. So what I'm going to do is for now comment this out and run this. So for all other other two, we do get the same class as what we had before. Now for the categorical naive Bayes, we'll create another data set np.random np.random uh, dot random integer 2, and then size is equal to 3 by 7. We'll keep the same shape as what we have been using earlier above. Then we have y underscore train is equal to np dot array, and here we have categories 1, 2, and 3. Earlier, if we look up here, we in where did it go? Okay, right here when we had a category, we just had two values. Here we have 3 different values, and so clf dot naive underscore Bayes, clf is equal to clf in naive underscore Bayes was categorical naive Bayes, and then clf dot fit x underscore train, y underscore train, clf dot predict x underscore train, and we'll just use the train here, the 0 to 1 and colon. So we are looking at all the columns and the first row. So we get a classification as 1 in this case, which matches the classification for a y train that is right there. Now moving on, let's look at how we can implement the Gaussian naive Bayes. So we have Gaussian naive Bayes, and for this we are going to use the data frame, which is this one, which is the weight, sugar content, size of apples. And so we create the x train is equal to np dot array, and we are going to drop the last column, so df dot drop sold, and that's going to be from axis, so 1 because it's a column we are dropping. And y underscore train is equal to np dot array, and this is going to be just the column sold, and we'll reshape this as -1. And then we have x underscore test is equal to np dot array. This is a test sample that we are creating, so 90, 20, 70, and we'll also create a y test for this. So y underscore test is equal to np dot array and the value of 1 there, so belonging to class sold. We already are saying that it's going to belong to class sold, and we are going to see if it prediction is in that order as well. Now for the type and sizes, why don't we copy this, paste it here so we know what they are. So we have 6 by 3 and 1 by 3 matrix clf, and sorry about that. Now for the classification, we can write the code here. clf is equal to naive underscore Bayes dot Gaussian naive Bayes, and clf dot train, and here we have x underscore train, y underscore train, and then we have y underscore pred is equal to clf dot predict x underscore test. Now we can print the values y underscore test. So what the value is for y test, we know it's 1. And then we have y underscore pred. So we are looking for the values of the y pred and see what those are. So Gaussian Naive Bayes has no attribute train. So let's see what happened here. Naive Bayes, B-A-Y-E-S. Let me copy this. Usually in this case it's a typo. Gaussian Naive Bayes clf.fit. That's my mistake. And so here we get a prediction of class 1, and that's how the Gaussian naive Bayes classifier works. So I hope in this video you got some intuition about how the naive Bayes classifier works. So what is naive, and how is it different from the normal Bayes, where because in this case we assume conditional independence between features. Then we looked at examples of Gaussian and multinomial naive Bayes and walked through them, as well as we looked at the implementation of all naive Bayes methods that we had in Scikit-learn on our toy examples. In next video, uh, we'll look at a new topic on decision trees, and I'm sure you'll find that exciting as well. And we'll cover the real world example of the naive Bayes methods in one of the projects in future videos as well. I hope to see you in the next video. Please like, share, and subscribe. If you have any comments or suggestions, please let me know in the comment section below. Thank you.